No, of course not.
My goodness.
Okay.
Let's look at number 19. Let's start there today. So, we'll answer a few more spring questions, but we kind of already covered the whole idea. It's just that springs have this linear behavior, and so if you just take that into account on any question involving a spring, you can usually figure out whatever you're trying to figure out about it with a little bit of algebra. So I just want to clarify maybe just one or two more of these, and then we're going to move on to the dreaded Atwood machines. Yeah, that's the last little subsection of this problem set. Atwood. So if you go to number 32, the top of that page says Atwood machines. And they're not machines probably in the sense that you guys think of a machine. It's just a pulley and two masses. Technically it's a machine, but usually when we think of machines, we're thinking of something that either electronic or gas powered or something. But, okay, so anyway, 19. So springs. And by the way, all this stuff we're gonna kind of circle back to it. So if you're kind of like, oh man, we didn't spend very long on friction, that seems kind of a big deal. It is. Same with springs. You're like, oh, aren't springs? Springs are actually super important. I mean, if any of you guys end up going into some sort of physicsy field like engineering, you're going to find that they model lots of things like a spring. So almost anything that vibrates, you kind of model it like a spring. So we'll get into that later. Even an atom can be seen in some way as kind of like a spring, kind of like a three-dimensional.
Spring theory.
Spring. See, Caleb, take notes. That was actually pretty good.
I was waiting for a little bit of conversation.
No. Constant credit that you never have.
Okay, so anyway, right now this is all just static stuff. So statics are always simpler than dynamics, meaning if the thing is just hanging from a spring, it's much easier to analyze it if the thing is jiggling back and forth on a spring. So anyway, that's down the road. So on 19, it says Bob hangs a spring from the ceiling. So here's his ceiling. He's got this spring, and he hangs a mass from it. And then what he's going to do is just change the mass. So let's say he keeps just adding on little bits of mass. There's a little attachment here. And what's going to happen as he adds more mass? The spring's going to stretch up. Okay, so then he graphs his data. He's got the spring's length here in centimeters. And then he's got the spring's mass here in grams. So by the way, what's the first thing you notice about these units? Yeah. Exactly. Very good. So the first thing you got to notice on something like this is you go, obviously I'm going to have to convert these numbers to meters and kilograms. So anyway, so what's the significance of this number here? Yeah, that's the natural length of the spring. That's the length of the spring if nothing's hanging from it and it's just sitting there. Okay. And then we can see that we're not really exactly sure how many data points he took. Maybe it was 5 points of data, maybe it was 4 points of data, but in any case, eventually he had 500 grams on there. And the length was 50. So do we feel okay about that? So, who's got a thought on maybe an equation we could write?
Take the initial of 20 or y equals x plus b.
You could do y equals mx plus b. I think we can go simpler than that because the question's just asking us to find the spring constant. So what's an equation I might write if I want to find the spring constant? Yes, so the spring constant, the definition of it is the change in force. How much force was produced for some change in the spring's length? Well, that's a bit of a, I mean, in some cases, there's sort of a chicken and egg thing going on because you're like, well, did the force cause the change in length or did the change in length cause the force? In this case, I'd say adding the extra force caused the spring to change length, but then hand in hand with that is when the spring's length changes, the spring is able to produce more force. So it's kind of a circle of cause and effect. So anyway, we got to figure out, how do I get this change in force?
Would you take your initial or your final minus initial?
You got it. So take the final mass. What does this correspond to? That's a mass, not a force. But that mass was hanging, right? So how much force corresponds to this much mass? Very good. So what you're going to do is, I mean, if it helps, you could do a little before and after picture. You could say, when there was 0 kilograms, what was the length back when it was 0 kilograms? So I'm going to say 0.2 meters. Does that make sense? There's the before. Here's the spring all stretched out. How many kilograms are attached? 500 grams. 0.5 or 1/2. However you want to think about that. It's half it. Everyone understand that? Divided by 1,000. Right? It's grams to kilograms. So half a kilogram, and then the spring was 0.5 meters. Sorry, this marker is kind of not very dark. All right, you guys finish the problem. I gotta get more markers. BRB.
Oh my gosh. Where's my sister? She's like ice cube.
You got it.
Did you use it?
Yeah. You did definitely.
Well,
So you basically get more smart and you go, sure.
okay.
Just get really close to taking.
Okay. Who got the answer? What? Here, I'll make this a little bit darker.
The average length is changing.
Just.
Okay, so how much force was the spring exerting when there was nothing attached to it? 0. So this corresponds to 0 newtons. This guy right here, well, this would be, mg would be 0.5 times 9.8, which is 4.9 newtons. Everyone okay with that? So that means that's exactly how much force the spring was exerting as well. So the spring exerted an additional 4.9 newtons, and that corresponded to a change in length of 0.3 meters. So my formula, I would write K, the spring constant, the change in force, like we said, was 4.9 newtons. The change in length was 0.3 meters. So calculator is helpful here.
It's 16.
Okay, Okay, so 16.3 roughly
Repeating.
newtons per meter. Okay? That's all there is to it.
I mean, I'll just.
We both know.
Okay.
It's like gravity does not exist.
Deputies are dead.
So, maybe we could just briefly talk kind of generally about like, Bob and his four-wheeled vehicle. Sorry, number 21. What's the only real difference between this problem and Bob getting in his four-wheeler? There's 4 springs instead of 1 spring.
That's the wings.
Four-wheeler's only on one spring?
What?
Isn't we?
No, in number 21, in this problem we just did, there's only 1 spring. So you'll have to, for 21, you'll have to think about it a little bit, but there's 4 springs sharing the force. Okay. So there's a couple ways you can maybe go about thinking about this, but when you think about when you go to do your change in force over change in length, it's going to be slightly different because there's 4 springs working together. Same thing with, if you look at like number, say 26, 27, 29, 30, and 31, all involve what happens when you have multiple springs. Okay. So,
Basically, you do the same thing for 19. Find a K, or spring constant, and then you divide by how many? 3?
well, I'll give you a quick example here. I mean, maybe let's jump forward and look at one. Let's do one where we actually figure out where we're not solving for spring constant. Let's look at 27. That's a good one. I guess we should also do 28 together because that's kind of a famous one. So let's do 27 and 28, and then we'll discuss Atwood machines a little bit. So for 27, try to get that set up. Maybe draw a force diagram, but it says each spring has a spring constant of 800 newtons per meter. That's pretty strong. They're hanging from a ceiling with a bucket attached. If we wanted to lower the bucket 40 centimeters, how much mass would we have to add to the bucket? That's the question. And there's 2 springs. And there are a couple ways you could go, kind of reason out the answer to this question. So let's start maybe with a force diagram. And then maybe before I draw the force diagram, consider this for a second. This is true, right? This is our definition. Is there any reason why I couldn't maybe rewrite this as kind of like that? That's fine, right? Now, what you would find in a lot of texts, or if you Google like spring constant, you might even find the formula written like this. Looks simpler, right? But just bear in mind that if you do this, then they're very careful to put like a caveat here that if you write it this way, x is the displacement from equilibrium, which is often a little confusing, but it means you can't now, I'm sorry, this is supposed to be an L, wasn't it? So if you're looking at, the length of the spring versus the displacement. So what I mean by that is, here's my spring. What's the length of the spring? Maybe 10 centimeters, right? What's the displacement? 0. So if you write it this way, x is the displacement, and then so when I go to stretch it, okay, so I can think of the stretching as being like, I'm going from 10 centimeters to 13 centimeters. or I could think of that as a 3 centimeter displacement from equilibrium. So if you think about that, you'll realize, oh yeah, that's the same thing. Because when the spring's in equilibrium, it's zero force. So these would be the same. Okay, so let's get into 27 here. Force diagram. Okay. So, there's some force, there's basically gravity pulling down, right? And there's two vectors pulling up. Is there any reason to think that those might be different sizes, those two arrows? No, it's totally symmetrical. So what you have basically is those adding up combined has to equal mg, right? And so if we talk about, say, adding some mass to the bucket, well, let's look at this. This kind of thing. Or this, however you want to think about it. But I don't know, let's use this. If I add some mass m to the bucket, what's the change in force that we're getting? So if I add amount m to the bucket, what's the additional force being exerted downward? Please. mg.
Okay.
Right, m times g would be the extra gravitational force there. Okay, so if I'm using that idea, okay, so pretend that we just added. All right, we're going to add in there. I don't know, we can call it capital M, I guess. We're going to throw that into the bucket. So the additional force exerted on the bucket would be m times g. Okay. So now, if I go, well, what's my k value? 800. And what's the desired change in length that we're going for? 0.4 meters. Everyone okay with that?
Wait, your spring con? Should be 2 times that since there's 2 springs.
We're gonna get there. So yes, what I'm doing, if you look at this setup, you're going, well, isn't that just, if that was one spring, right? So the answer we're gonna get here would be, that's the amount you'd have to add if there was only one spring pulling. But since there's 2 springs, it's only gonna be half that mass. But Caleb makes a good point. Couldn't I kind of think of those springs as working together so I could double the K value? Make it 1600? That's the same exact approach, right? So that's what I mean by, like, there's different ways you can kind of go about thinking about this. So I don't know, does that make sense? Okay, so what's the answer? Again, this is a pretending, like, if it's just one spring we're thinking about, the mass, that looks kind of like a mu, sorry. The mass would be, anyone have a calculator? Tell us what that is.
Oh, yeah, it's like 30 something with the rate.
Huh?
It's 32.
32 exactly?
Oh, I'm at 0.
No. You gotta divide by G. It's gonna be 30 something.
32.7.
Yeah, it's called 7. Okay, now again, that would be if it was just a single spring with spring constant of 800. Make sense? So what's the actual answer?
65.4.
Why would you double it, not theta?
there's two springs and they're both exerting. So let's go back to this. So this quantity here is how much force each spring would exert if you stretched it by 0.4 meters. So let's look at that number, 320 newtons, right? So now if each spring is providing 320 newtons, do you see how that's basically doubling the force upward? So that means I would need double the mass that I would need with one spring. By the way, let's think about this a different way. Hope I'm not confusing you guys. I'm trying to show you there's different ways you can approach these problems. I don't want to prescribe one. There's only one way to do it. There's a whole bunch of ways you can reason these out and think about them. So sometimes students will come up, they'll have some way of thinking about it, and they're like, oh, it didn't occur to me. So I'm trying to encourage you to think about these sort of flexibly. But anyway, what if I just totally focused on these two numbers and said, how much force does this spring generate? How much extra force does it generate when you stretch it 0.4 meters? Well, the answer to that is each one's giving you 320 newtons. So now my force diagram says 640 up. So how much force down was there? 640. So if I solve that, if I say, okay, well, this is equal to mg, and I solve for m, I get 65.4. So maybe that approach makes more sense. So the first way we did it was kind of like, well, pretend it's one spring in your head. Pretend it's one spring. See how the math works out. Then go, well, two springs is twice as strong as one spring, so you have double the mass. Or the other way to think about it is just to first look at how much force each spring will be generating. We feel okay about that? All right, so take a minute. Read 28 carefully. This is an exercise in technical reading, I'd say,
All right, I'm gonna get to AIP.
You don't need to annotate it, you just need to read it and understand what it
That is
says.
the best sentence I've ever heard.
All right, has everyone had a chance to read it? Okay. Who can explain this maybe in simpler, less precise language, just like in simple terms? Can anyone do that? Anyone? Yes, Aiden.
So you took a block that was attached to a spring against a wall, and then you aggressively stretched it out. But when the spring hit its max thing, every time you took it out more, it just came back to its max.
Excellent. Perfect explanation. Okay. Everyone understand the scenario? Sure? Okay, so the question is, all right, like given that, it's kind of a contrived scenario, but what would be, if you knew those values, so if you got this wall, here's this frictiony surface, and basically, does it make intuitive sense to you why if the spring was only like a little bit stretched out, then there'd probably be enough friction force to just hold the block in place? But the more you stretch the spring, the more force it tries to pull back with. And eventually that spring force is going to overcome the friction force, right? So, so let's see. What does X represent?
Another position.
Yeah, X is that eventually, say we keep doing it, right? Eventually, we're gonna find that there's some distance X that's the farthest you can go before it starts sliding back. That's what it says here. X is the maximum distance you can pull this thing before it starts to slip back from the spring. Mu is the friction coefficient. Okay. Oh, so by the way, let's look at this. How much have I displaced the spring? X. So what's the spring force? How much spring force is pulling back? Very good. X times K. Does everyone understand that? Okay. Because when the spring was in equilibrium, there was no force. So the additional force would just be K times the amount you change the length of the spring. So just to clarify, this is where if you've wrapped your head around this way of saying it, it's very direct. If you're still thinking about it in terms of this, it still should make sense because it's the exact same concept. But in this case, you have to make some kind of logical leap to say, well, the change in length of a spring is X. And the change in force actually is the force you end up with. So, all right, what is this vector here? Friction. That's friction. Now, how big is the friction force? Mu times. Yeah, so don't forget, let's make the whole force diagram. There's mg pulling it down. The floor pushes up with mg, that's called the normal force. And so the friction force is mu times the normal force. Cool beans to everyone? All right, now. Pretty complicated picture, right? But let's test our mathematical intuition. Is the rest of the problem easy or hard?
Easy.
It's easy. Despite the appearances, because what's all we gotta do? It's okay if you don't find it easy, I'm just saying. If you're, well, even simpler than that, look at the force diagram. What am I about to write? Here's a hint. There's gonna be an equal sign in it.
Kx.
Kx
M or mu
equals mu mg. So you see what I was talking about? So all I had to do was notice that, well, my force diagram is balanced. Why is it balanced? Where's that fancy word? Is it in there? Maybe not. I didn't say static equilibrium, but it is. It's static. It's in a static equilibrium. So what am I solving for, by the way? Mu. So when I solve this,
just do Kx divided by
look at that. Now that look at how concise that is. This is one of the things I think is really amazing about physics, math, and science in general. This describes this very complicated scenario, but very elegantly. It's very, very, only got a couple symbols. How many symbols? 5, 6, 7, 8 symbols. So pretty minimal, really. Or is it 7? 1, 2, 3, 4, 5, 6, 7 symbols. So there you go. So that describes this relationship where if you have a spring fighting against friction in this particular scenario where it's like you need to maintain static equilibrium, and this number is the largest displacement allowed while still maintaining static equilibrium, then this is the relationship between all those quantities. Okay. How are we done for time? Oh, great. Okay. Do you guys feel okay on friction, like generally speaking? Okay, so you can just, everything comes back to this idea. So if you can kind of wrap your head around that, then you'll be good. I feel like we may, after you guys attempt them, we may need to clarify on 29, 30, and 31 possibly, because those can be a little tricky when you have multiple springs. But just realize that like when you have 3 springs working together, that's going to be triple the force versus the 1 spring. And 2 springs is double the force of 1 spring because it's 2 springs pushing together in the same direction. If you draw a force diagram, you can see that, yes.
So essentially the same process when the strings are being compressed, correct?
Mm-hmm. Yes,
It's
exactly.
still just this change in length or
Yes, totally. Same exact formula. So if the spring's being compressed or stretched, doesn't matter. All right, guys, can we move on to, can you do an intro on Atwood machines? You okay with that, Julia?
Sure. I mean, yeah.
Well, we have more questions on springs, if anything's unclear about how they work.
Wow.
That was better than the average firm. You gotta give him some credit. That one wasn't quite as terrible as his usual ones. Okay, so
God.
you're gonna be gone tomorrow?
And Monday and Tuesday.
Why, bruh? What are you gonna hunt for?
Here's anything with lux.
Do you can you get a elk tag like every year, or is that a hard one to get? Okay, it's easy to get that.
Yeah, you can fight over the.
Okay. What am I thinking of? That's the hard one to get, like moose or something.
Moose, antelope, antelope depending on what district you put in for, and then like big bird sheep, mountain goat.
yeah.
Humans.
Yes.
I heard there was a national park somewhere that they wanted people to come in and like shoot as many goats as they could.
Yeah, I think that's, it's one of the national parks in Wyoming. I think it's, I want to say the Teton. Yeah, but.
Mountain goat.
I'm trying to remember what animal it was that.
Yeah, it was, the elephant and the buffalo, they shoot buffalo.
I'm trying to remember what animal was like. Wasn't it Dave Windauer just got a tag? And people are saying it was like it's so hard to get that tag. I'm trying to remember what it was. I thought it was an elk, but I guess I was way off.
It could be, there's some districts that are like super hard in other
Moose?
states. to get.
Wait, what, Robert Moose?
It was just I know that Dave Windauer got a tag.
Moose.
Yeah.
It was a moose.
Yeah.
Oh, okay.
Yeah,
Poor
he said he was literally circling a tree with a moose because the moose was.
Charging him.
Oh, he had a confrontation with moose. And I'm talking about he hunted this animal that he got a tag for it. I just remember someone mentioning like, oh, it's really hard to get that
He
tag
shot the moose with his bow.
after he had this standoff with it.
No, before.
And then
He shot the moose, and then the
He
moose.
shot the moose, chased after it, and then the moose goes, "Ha! I got you now!" And run at him, and he goes.
And you did the little circling on the tree until the moose bled out.
Yep.
Wow.
Oh my God.
But like getting the archetype of moose.
I would have pissed my pants like 20 minutes.
Yeah.
take that
Oh my
out.
goodness.
I would take it down.
This is it.
This is it.
Well, the moose tags are really hard to get.
Okay, so
Did you know that a moose can swim up to 20 feet underwater?
Can you imagine a short one?
Nowhere is safe.
all right, guys. We're going to we got to cover this thing here. So especially if you're gonna be gone tomorrow. So I guess I'll try to squeeze both in here. So the Atwood machine, it's a really famous sort of thought experiment in physics, and you'll probably see. Hopefully, you'll understand why it's considered so, I guess, important to like understand this kind of thing. It tells you about how to like model a system that's not very obvious, okay, not intuitive. So, because it's way less intuitive than the static system. Because you'll notice this question says you have the 20 kilogram block right here, and you got this 5 kilogram block right here. And it says when you release it, now it says this is frictionless, by the way, if you missed that. Friction. Okay. So wait a second, if that's frictionless, can this thing ever be in static equilibrium? If this has some mass. No, even if this was like 0.1 kilograms, it's still gonna exert some tension on the string and pull the block towards the edge of the table. So the question is asking, what's the acceleration of the system and what's the tension in the string? So, all right, let's get into it here. So what's something obvious we can figure out from this diagram?
Yeah.
We can get the normal force. Yeah, those are two good points. So we can get the normal force on this block. So this guy has mg normal force, but the table just cancels those out. So, okay, so for the sake of completeness, that's good to put on there. But if we throw friction in here, that's going to be hugely important, right? Like in the problem we saw before, that was the key to solving the problem. So in this case, so it's frictionless, so the normal forces gets canceled out. We can certainly get this number. This would be mg, 49 newtons. Now, here's the really confusing part. How do I phrase this? There's a wrong answer to how much tension's in the string, but a lot of people think that's the answer. What do you guys think is the most common wrong answer right now in the problem? They say 49 newtons. And then you go, but that's not possible because we know just logically that the system has to accelerate, right? So how can the tension be 49? If the tension was 49, then the net force would be 0 and he wouldn't accelerate. So it's a contradiction. Here's what you do. You say, I'm just going to call it T, T for tension. Okay. And then now, how much tension is in the string up here then? It's the exact same T. That's the key here. It's the exact same value. Does that make sense? Okay, so let's write our famous equation. So ignore him for a second. Couldn't I write an equation describing this? So this is the famous F net equals MA. So how do I write? By the way, what direction should I call positive, you think, for this problem? That would make the most sense. This way, right? Because that's the direction it's going to accelerate. So let's call that the positive direction. So if that's the positive direction, then what's the expression for net force? 49 minus the tension equals the mass times the acceleration. Who's confused? Sorry, there's some weird glare here. Hopefully that's visible. Sort of, kind of. Okay. That makes sense though? So the net force is 49 minus the tension, and the mass is 5, the acceleration is. Now, what's the problem though? There's two variables. Well, hopefully your Algebra 1 class has stuck with you and you go, wait, there's two variables, I need two equations, right? You're a thinker, yes. Luckily, there's a second block that I could write an equation for. And also, here's the key, it's the same tension variable, right? Because that's how string works. And then 2, it's attached by a string to the other block. So won't his acceleration be the same number as his acceleration? So same T, same A. So let's write his equation. His F net equals MA. What's his net force? T. That's the only vector, right?
Yeah.
And be super careful though. In the first equation, do you see how T was negative because it pointed away from the opposite direction? But up here, this is the positive direction, so T is positive. It's very, very important to understand that. And then, so that's the whole net force, and so net force equals MA. Okay? So now, I can use substitution or elimination. It's up to me. Sure. Let's show both. How about this? Let's do elimination first. Elimination means if this equals this and this equals this, then this plus this has to equal this plus this. Right? That's what elimination says. So let's add these together. Does that make sense?
That was kind of fast.
Okay, so elimination says, I'll communicate it in a much higher level language. If Apple equals, let's all use emojis. If Apple equals smiley face and what's another emoji?
Butter.
Butter.
Butter is an emoji?
Yeah.
Okay, and butter equals hockey player, okay, then it stands to reason that this plus this
Letter apple.
equals
Ah, yes.
this plus this.
Better.
I found over the years, I found that a lot of students, they know maybe elimination, but they don't understand the very basic logic behind it. That is literally all elimination is. You're saying, I can say these are the same and these are the same, so this plus this must be the same as this plus this. That's all you're doing. Okay. Just wanted to clear that up for any confusion. Okay, add those up and you get 49. Add those up, 25A. So the answer for A is 49 divided by 25, which is that 1.96 meters per second squared. Oh God, how do I find the tension?
Plug it in.
Oh, I can plug it back in here.
Wow.
Wow. So just plug it back in now. There's your substitution. Well, it's a substitution. And you get tension. The tension would have to be, so let's say 20 times 1.96. What is it?
39.2.
Now, think about those numbers. Does that number make some intuitive sense? That 49, Newton's pulling him down, 39.2 pulling him up. Okay, so the net force on him would have been, well, what do you get, 9.8? Yeah. Right?
Yeah.
Which gives you the net acceleration of 1.96. So, oh, by the way, for those of you going, well, I wanted to do substitution, not elimination. I hate elimination. Well, that's fine. You would have just taken this before all this bad, scary stuff happened. You would have gone. This t is equal to 20a, so you would have plugged that 20a right in there, and just you would have had 49 minus 20a equals 5a, and lo and behold, the miracle of mathematics, you end up with the exact same equation. Yay. All right, cool beanies. We're out of time, so I will cover tomorrow the scarier Atwood machine, which is when they're both dangling.